morning. Welcome to the second lecture on pattern recognition and image understanding. So, in our first lecture, we have discussed about what is a pattern recognition problem and how to recognize the pattern. Okay. So, let us take a very simple example to start with. Suppose we have a circular arc, say something like this. Okay. So, this circular arc is also a pattern. Similarly, if I have some function, something like this, some variation of signal, so you can say this is a signal which varies with time. So, I can say that it is a function ft which varies with time t. So, this is also a pattern. Now, given different such patterns which may be similar or which may be dissimilar, how do we say that two patterns are similar or two patterns are dissimilar? That is the basic problem of pattern recognition. So, whenever I say or I can find out that one pattern is very similar to another given pattern, then I say that the first pattern is recognized as the second pattern, which is nothing but the knowledge that we have or something that we have in our knowledge base. Okay. So, coming to this simple problem, say circular pattern recognition. So, given two circular arcs, one circular arc is like this, the another circular arc is something like this. So, how can we say that these two circular arcs are same or they are part of the same circle? So, as you know that if we go to parametric domain, a circle is defined by a parameter which is nothing but the radius of the circle. And if I do not consider the case of translation invariance, then I will have two parameters, one is the center of the circle and other one is the radius of the circle. So, if I describe a circle only by the radius, in that case the circle is translation invariant. Whereas, along with radius, if I also specify the center of the circle, in that case the circle is translation invariant, because the moment I translate the circle from one location to another location, its center is going to change even though the radius will remain the same. Okay. So, that is why we have different kinds of features, the translation invariant features, rotation invariant features. Of course, if you rotate a circle, the features will also remain rotation invariant. Whereas, once I specify the center of the circle, it is no more translation invariant, because the moment you translate the circle or you shift the circle from one position to another position, the center of the circle is going to change. Okay. So, given these two circular arcs, if I want to say whether these two circular arcs are same or part of the same circle, or these two circular arcs are similar, then what I have to do is I have to find out what is the radius of the circle, I have to find out what is the location of the center of the circle. Okay. So, naturally, to find out the radius of the circle, it is a matter of school level mathematics. What we will usually do is we will try to find out a perpendicular at one point on the perimeter of the circle. So, you draw a perpendicular like this. Similarly, you take another point on the perimeter of the circle, you also draw a perpendicular to the circle at this particular location. Okay. And the point of intersection of these two perpendiculars is nothing but the center of the circle. Okay. And once I get the center, then finding out the radius is very simple. It is nothing but the distance of a point on the perimeter from the center. So, I can easily find out the radius and I can also find out the center. Similarly, if I perform the same task for the second circular arc, I can find out what is the location of the center, or taking perpendiculars from 2 points on the circle, I can find out what is the location of the center, and once I have the location of the center, I can find out what is the radius of the circle. Okay. So, in this case, let me call it, this is radius 1 because it is of the first circular arc. Let me call it as center 2 because it is center of the first circular arc. Similarly, in this case, let me call it as radius 2 because it is radius of the second circular arc and the center of the second circular arc. Okay. So now if I find that radius 1 is same as radius 2, these two radii are equal, and in most of the cases I cannot get the condition that these two are exactly equal because there is error of quantization, error of measurement. Okay. So because of those error, and similarly there is also error in segmentation. Okay. It is very difficult to get perfect segmentation. If the segmentation is erroneous, then obviously the position of the circular arc or the points which belong to the circular arc, they may deviate by 1 or 2 pixels. So in such case, it is extremely difficult that even if they are part of similar circle, the radii are same, but after doing this computation, radius 1 may not be exactly same as radius 2. Okay. So what I have to do is I have to find out a measure of similarity, which is nothing but what is the difference between radius 1 and radius 2. So if I find that the difference between radius 1 and radius 2 is very small, that is negligible, I assume that they are same. Okay. So in which case I can say that this circular arc is C2 and this circular arc C1, they are part of the same circle or their radii are same. Okay. Whereas if the positions of the centers are different, then though the circles are same, these two circular arcs are not part of the same circle. Okay. So one circle is translated with respect to another, right? Whereas if I have a case something like this, okay. So here what I am trying to do is I am trying to depict a case where I have two different circular arcs of the same circle, but these two circular arcs are not connected. They may not be connected because of various reasons. I can have a situation something like this. So I have a circle, but on this circle I have another object. So this part is occluded. Okay. So this object is on top of the circle, and when I take the image from top side, naturally this part of the circular arc and this part of the circular arc or this part of the periphery will not be visible to the camera. Okay. So once I do this segmentation, I'll get a situation something like this. So though these two circular arcs are part of the same circle, but they become discontinuous. Now in this case, if I want to find out whether they are part of the same circle or not, I'll perform similar type of operation, find out the centroid location of the center, and here you will find that the location of the center considering this arc and considering this arc, they will be same, or they may not be exactly same, but they will be very close to each other, or distance between these two centers is very small. Okay. Whereas, so in this case the center will be very close and the radius, the length of the radius will also be similar. So in this case we can say that both these circular arcs are part of the same circle. Okay. So what I am trying to do is, whenever I want to recognize a pattern, what I have to do is I have to extract certain features of the pattern, and using those features in the feature domain, I have to find out whether the patterns are similar, the patterns are same, or the patterns are different. Okay. So over here in this particular example, I have taken, this is a very simple case of circular arc. So I have simply calculated the length of the radius and the position of the center. Okay. Whereas over here, this is not a simple pattern like a circular arc. Okay. So in these cases, we have to find out that what are the kind of features that we should be able to extract, which is useful for recognition purpose or which is useful for classification purpose. So that given another pattern of similar form, I can say that this pattern P1 and this pattern P2, whether these two patterns are same, they are similar, or they are widely different. Okay. So this pattern recognition problem is nothing but a matching problem. So whenever you find that the similarity between two patterns is very high or the dissimilarity is very low, in that case, taking one of the patterns as a reference or as a model which is there in our knowledge base, I say that the second pattern is recognized or associated with the first pattern. Okay. So in any recognition problem, I have to have a set of knowledge or set of model, and given an unknown pattern, I have to identify that unknown pattern with one of the patterns which is known to us. Okay, that is basically the pattern recognition problem. And to generate these known patterns, obviously, as I said, that we have different kinds of learning. One is supervised learning and the other one is unsupervised learning. Okay. So in case of supervised learning, I have to have a set of patterns which are known. Okay. So set of similar such patterns, maybe this pattern is generated by some measuring instrument. Okay. So I have to take similar such patterns from the same measuring instrument, a number of such patterns, and whatever feature I extract for one pattern, I have to generate similar features for all other patterns. And using these features, I have to generate a model. That is a feature vector which is representative of this class of patterns. And that is the representative feature vector which is to be kept in the knowledge base. So anytime a new pattern comes, I will generate similar such feature vector and compare these two feature vectors with what is the distance between these two feature vectors. So if the distance between the two feature vectors is very small, I will say that this unknown pattern is same as the pattern that I have in my knowledge base. If the distance is large, I will say this unknown pattern is different from the pattern that I have in my knowledge base. Okay. So in case of supervised learning, what I have to do is I have to take a set of known patterns for which I have to find out the feature vectors, and for those feature vectors I have to form a representative feature vector which represents the same class of patterns. Okay. So that is what in case of supervised learning, which makes use of known patterns for training or learning. Okay. And another class of learning or training which is unsupervised learning. So what is the difference between supervised learning and unsupervised learning? In case of supervised learning, we have to make use of a number of known patterns for training purpose or for learning purpose. So the classifier or the recognizer learns using a set of known patterns. In case of unsupervised learning, I don't have any known patterns. Okay. So I'll have patterns like this. Similar such patterns may also be there. Okay. I can have some patterns of this form, similar pattern again of this form. Okay. In case of supervised learning, you know that these two patterns are similar or same, though there may be slight deviation. And these two patterns are same. This set of pattern and this set of pattern, they are different. That is known in case of supervised learning. In case of unsupervised learning, it is not known. Okay. So you have a mixture of such patterns. And whenever I have a mixture of such patterns, naturally for all the classification problem, as I said, that I work in the feature domain, in the domain of feature vectors, not in the patterns themselves. Okay. So I generate set of feature vectors for each of these patterns. So what I have is a mixture of feature vectors. The feature vector may be generated from this pattern, it might be generated from this pattern, it might have been generated from this pattern, it might have been generated from this pattern. From wherever it comes, I just have a mixture of feature vectors without having any information of what is the source of that feature vector. In case of supervised learning, I know the source of the feature vector. So for unsupervised learning, what I have to do is I have to process those feature vectors, and by processing those feature vectors, I have to partition the set of feature vectors into a number of subsets, where the feature vectors in one set are generated from similar patterns. Feature vectors in another subset are generated from another set of similar features. Okay, so the feature vectors generated from these two classes will be going into one set, and the feature vectors generated from these patterns will move to another set. And this partitioning of the feature vectors into different sets have to be done by data processing. This knowledge is not known beforehand. In case of supervised learning, this knowledge is known beforehand. Okay. So once I partition the feature vectors into different subsets, then I can take the feature vectors from every set. So from set 1, I take all the feature vectors, and using those feature vectors, now I generate a representative feature vector, which in case of supervised learning, because I knew the class belongingness of the feature vectors, straightway I could have used those feature vectors to generate the representative feature vector. In this case, the first step, which was already known in case of supervised learning, that is not known, so I have to do it first, that is partitioning the feature vectors into different subsets. And once that partitioning is done, I have to take the feature vectors from every different partition, and using feature vectors belonging to a single partition, I have to generate a representative feature vector for that class of partition. Okay, and then going for recognition, the task in supervised learning, unsupervised learning, that remains the same. Okay, so only one step will be additional in case of unsupervised learning, that I have to go for partitioning of the feature vectors into different partitions depending upon similarity of the feature vectors. So when you do this partitioning, you have to make sure that all the feature vectors which are put into this subset S1, they are similar. All the feature vectors which are put into subset S2, they are also similar. Whereas if I take a feature vector from S1 and another feature vector from S2, these two feature vectors have to be widely different. They should not be similar. One step is less in case of unsupervised learning. In case of unsupervised learning, one step is more. That is, I have to do data agglomeration based on similarity, which I don't have to do in case of supervised learning, because in case of supervised learning, somehow that has been done. Yeah, that also learns, but what it is learning, that is known. See, in case of supervised learning, coming to the feature vector domain, suppose I have a set of feature vectors f1, f2, f3, f4, f5, f6, f7, and so on. Okay, suppose this f1 to f3, these are the feature vectors which belong to say class C1. Okay, and f4 to f7, these feature vectors, they belong to class C2. Right? In case of supervised learning, this is already told that these three feature vectors f1, f2, and f3, they belong to class C1. Similarly, f4, f5, f6, f7, they belong to class C2. That is told. So when I am training my recognizer, okay, recognizer has to make a decision that given a feature vector, what is the class belongingness of that feature vector. That is the decision that the recognizer has to do, right? So when the recognizer is taking this decision, so given this feature vector f1 or another feature vector which is very close to f1, which are widely different from any of these four feature vectors, that feature vector, the recognizer should decide that it should belong to class C1. Okay. So what in case of supervised learning you have is, you have the input, and for this input what decision the recognizer has to take, that is also known. Okay. So if the recognizer takes any decision other than the correct one, you know there is an error. Is that okay? So by making use of that error, your approach will be to train your recognizer in such a way that the error is minimized. Okay, there are different techniques for that. We'll discuss that later. So that part, the class belongingness of the training samples or the training feature vectors, which are known beforehand in case of supervised learning. Similarly, over here, if F4 is presented to the recognizer has to take a decision that F4 belongs to class C2. But if the recognizer decides that F4 belongs to class C1, that means I know there is error. So to minimize this error, I have to perform something. Okay. So that is what is learning or training of the recognizer. In case of unsupervised learning, I simply have this set of feature vectors. I don't know whether the feature vectors belong to class C1 or the feature vector belong to class C2. So straightway, I cannot give this F1 to the recognizer and expect that the recognizer will give me an output which I can understand. Okay. So that is why I need a pre-partitioning of the feature vectors based on similarity of the feature vectors. You can say this is a sort of pre-processing. Okay. Now after doing that, all the feature vectors which are in same partition, I know they are coming from the same class, though I may not know what is that class. Okay. In case of supervised learning, I know what is that class. In case of unsupervised learning, I may not know what is that class, but definitely I know that they are coming from the same class, whatever class it is. Is it okay? So that is how I can form, but while doing this partitioning, what I am doing is I am making a sort of class association of a set of feature vectors. Okay. And once this partitioning is done, then by making use of this, I can go for recognition purpose or training of the recognizer, and following the training, the recognizer can be used for pattern recognition. Okay. So this is the difference between supervised and unsupervised learning. So in case of unsupervised learning, I have to have this job of partitioning of the feature vectors into different partitions or different subsets, and once that is done, the remaining of part of learning will be same as in case of the supervised learning of it. I am coming to. So for determination of these feature vectors, the simple example I have taken is for circular arcs. Okay. What feature vector you have to generate, or what are the features that you should look into, that depends upon your problem. Okay. If I know that all the patterns that I am going to get, they are basically circular arcs, then features I will try to generate is simply the radius and the center, because given the radius and the center, that uniquely determines the circle. I don't need any other information. If it is an ellipse, then radius and circle is not sufficient, isn't it? I have to know the parameters a and b, because x square by a square plus y square by b square, equation of an ellipse, is it not? So I have to know what are these parameters a and b. So what are the features, or what is the feature vector that you have to generate, that depends upon your problem domain. Okay. Because every feature is not equally acceptable for every pattern. Depending upon the pattern, I have to decide what kind of feature I have to look for. And in many cases, given a pattern, I can uniquely find out a feature vector, or I can uniquely find out a feature. But given a feature, the same pattern may not be generated. I may not be able to generate the same pattern given a feature vector. Okay. So your feature vector to pattern mapping, that is actually one to many. It is not unique. But given a pattern, if my procedure for generation of feature vector is fixed, I will always generate the same pattern, same feature vector. So the mapping from pattern to feature, that is unique, whereas mapping from feature vector to pattern, it is not unique. Is it okay? So because it is not unique, so many patterns may be mapped to the same feature vector. Then the question comes that if many patterns are mapped to the same feature vector, then using the feature vector, how do I distinguish the pattern? Okay, and this is the only reason that we don't talk about features, but we talk about feature vectors. Okay, feature vectors will definitely have different components. Every individual component tries to capture some property of the pattern. Okay, so all these components taken together in the form of feature vector to some extent pinpoints to a particular pattern, though may not be unique even in that case. But I can have a smaller set of patterns which will generate the same feature vector. As you reduce the dimensionality of the feature vector, this set goes on increasing. The size of the set will go on increasing. Okay. So in all these pattern recognition problems, we never talk about a single pattern, but we always talk about a single feature, but we always talk about feature vector. And the feature vector has different components, where every component tries to capture a certain property of the feature of the pattern. Okay. So coming to the case of the feature extraction or the descriptor extraction. Okay. As we said in the last class that we can have two different types of features. One is shape feature or shape based feature, and the other one is region based feature. Okay. So this shape feature simply tells you what is the shape of the object, whether it is a rectangle, it is a sphere, it's a square, it's a circle, it's a ellipse, and so on, or it has some arbitrary boundary. Okay, so that is what is told by the shape feature. And the second kind of feature, that is the region feature, it talks about what is the region, what is the property of the region which is enclosed inside the boundary. Okay. So by this region, what I mean is, in simple gray level image, it may be the intensity values. If we have color image, it may be a color feature. Okay. It may also be texture feature if the region has different types of texture. Okay. If it is a colored texture, I can have color feature along with the texture feature. Okay. And even a colored texture can have different intensity values. Okay. So when we talked about color image processing, particularly in HSI model, we have talked about hue, saturation, and intensity, and we have said that hue gives you the color information, saturation gives you the purity of the color, and intensity is black and white equivalent of the intensity value. Okay. So if the intensity is high, the image will be bright. If the intensity is low, the image will be dark. So I can have within a region the texture feature, color feature, intensity feature, combination of all three, or any one of them. Okay, or any two taken at a time. So that is why I said that a single feature does not give you a proper description. What I have to take is multiple number of features, where every feature tries to capture certain property of the pattern, and all those features taken together in the form of a vector. And whenever I form a vector, the position of the element within the vector is very, very important. Okay. So I have to put these features in a particular order, and also I have to maintain the same order. Right? So all these features taken together, put in the form of a vector, to some extent pinpoints to a particular pattern or to a class of pattern where the domain of this class is very, very narrow. As you reduce the dimensionality of the feature vector, the domain will become wider, because more and more patterns of different types will come into the same class. Okay. So first, let us concentrate on this shape feature or shape based feature. Okay. So suppose we can have an arbitrary shape like this. Okay. And earlier we said that whenever we want to detect a shape feature, it is not necessary that I have to know what is there inside. If I know, or if I code only the boundary of this shape, that is sufficient to tell me what is the shape feature. Okay. Now, one of the kind of features or the descriptors which can be used to describe or represent this particular shape is what is called a chain code. What is chain code? Pardon? No. Chain code is, if I want to represent this boundary, an arbitrary boundary, by linear segments. That is some sort of linear approximation of piecewise linear approximation of arbitrary boundary. Okay. So if I want to represent this arbitrary boundary by piecewise linear approximation, then I can represent this boundary by linear segments of some specified length and specified direction. Okay. So if I represent this boundary by sequence of linear segments of specified length and specified direction, that is what is called a chain code. Is that okay? So when I say that I have to have linear segments of specified length and specified direction, so I have to specify it beforehand what is the length and what is the direction. Okay. So firstly, let me talk about how to decide the direction. This direction can be specified in either 4 connectivity or in 8 connectivity. I hope all of you know what is connectivity, 4 connectivity and 8 connectivity. So this direction can be specified either in terms of 4 connectivity or in terms of 8 connectivity. So if I talk about 4 connectivity, suppose I have a central pixel somewhere over here, then these pixels in 4 connectivity has 4 neighbors, one on top, one to the right, one at the bottom and one to the left, right. So when I want to move from the center pixel to any of these 4 connected neighbors, I can have only 4 possible moves. I can move towards east, I can move towards north, or I can move towards south, or I can move towards east. So these are the only 4 possible moves that I can make. Okay, and this is what is what I mean by direction. So if I specify that this I code as direction 0, this I code as direction 1, this west I will code as direction 2, and south I will code as direction 3. So you find that every direction is now coded either as 0 or as 1 or as 2 or as 3. Okay, so that gives me all 4 possible movements, directions in which I can move following 4 connectivity. Okay. If I go for 8 connectivity, suppose this is my neighboring pixel, I have these 4 pixels which are 4 neighbors, one to the east, north, west and south. In addition, I have these diagonal pixels, north, south, northeast, northwest, southeast and southwest direction. And now from the center pixel, if I want to move, I can move in any of the 8 directions. I can move either in the north, in the east direction, I can move in the northeast direction, I can move in the north direction, I can move in the northwest direction, or in the west direction, or southwest direction, or south, or southeast. Okay. So these are the 8 possible moves that I can make from the center pixel following 8 connectivity, right. So now if I code these movements as 0, 1, 2, 3, 4, 5, 6, 7. Okay. So following 4 connectivity, I have 4 directions, 0 to 3. In case of 8 connectivity, I have 8 directions, 0 to 7. Is that okay? So the directions are fixed. Now we have to decide about the length of the linear segment. I'll come to the length concept a bit later. Now let me see that how using these directions and assuming length to be 1, how I can go for coding the boundary of a shape. Okay. So suppose I have a shape something like this. So we are talking about chain code. Suppose I have a boundary something like this. Of this form. Okay. You find that can you see the grids? Actually, all these are placed on grid intersections. So suppose I start from any particular point, and let me assume that I scan the figure in raster scan fashion, and whichever is the first boundary point I reach, that is my starting point. Okay. Now once I reach my starting point, from the starting point I will move in the clockwise direction, or I will try to trace the boundary in the clockwise direction. So my starting point following the raster scan fashion is this one. Okay. I want to make a move from the starting point to the next boundary point in clockwise direction. Okay. So when I try to make a move, obviously I will move in this direction. Okay. And come to the case that if I assume that I am following this 8 connectivity, this particular movement is given a code 0. Okay. So here I will get 0. Next movement over here is in the southeast direction. Okay. And for southeast direction, following 8 connectivity, the code is given as 7. So this movement will be coded as 7. Similarly, over here, this is also 7. Again, southwest direction. This is in the southeast direction. Next movement is in the southwest direction, and southwest movement is coded as 5. Okay. So I'll code this as 5. Next one is in the south, which is coded as 6. Again southwest, coded as 5. Then in the west, which is coded as 4. One more west, which is again coded as 4. Then I have northwest, which is coded as 3. Then I have movement in the north direction, which is coded as 2. Then I have northeast, which is coded as 1. Okay. Then again I have movement in north, which is coded as 2, and then again a northeast, which is coded as 1. Okay. And this completes the tracing of the entire boundary. Right. Now once I have this, you find that this sequence of movements can be used as a descriptor of this boundary. Okay. So the sequence becomes 0, 7, 7, 5, 6, 5, 4, 4, 3, 2, 1, 2, 1. Okay. So this codes the directions of the linear line segments, and in this case we have In fact, here all the pixels are more than all the pixels have one neighbor. Okay, and if it is a boundary, then ideally the pixels will have only two neighbors. If it is a boundary, otherwise the third point that you have is an extraneous point, right? So I can have situation something like this. What you said is, so I can have a boundary of this form. So over here, something like this. Is it okay? So when I go for chain code, this has to be taken as an extraneous point, which has to be removed beforehand. And for removal of this, you must have heard about morphological filtering. Do just opening and closing operation, okay, and these extraneous points will be removed. Those who have done my course, I did not talk about the morphological operations. Okay, so by using the morphological filtering operation, such extraneous points can be removed. Similarly, I can have something inside also, so something like this, which may come due to noise. So again, by using morphological operations, such kind of noise can be removed. Okay. So coming back to this boundary is represented by a sequence of directions like this, and over here the length of the line segment is assumed to be 1, because I have moved from every pixel to its neighboring pixel. Okay. So this boundary is represented by this kind of chain code. Okay. And you find that the problem with this chain code is that instead of taking this as my starting point, if the starting point comes out with somewhere over here, then the chain code will be totally different. The chain code will be 5, 6, 5, 4, 4, 3, 2, 1, 2, 1, 0, 7, 7. Okay. So if I take this point as my starting point, then this is the chain code. If I take this point as my starting point, then this is the chain code. So the chain codes are totally different. Not only that, if the shape is rotated, then I have even worse situation. In this case, at least, even if the chain code is different, but the same symbols appear in the same sequence. Okay. But if the shape is rotated, let us take a very simple case. So I have a rectangle. Okay. And let us assume that the length of each side of the rectangle is my unit distance, right? And let me also assume, to make the situation even simpler, that instead of this 8 connectivity, I am considering 4 connectivity. Okay. So following this 4 connectivity and taking this as the starting point, the chain code for this particular figure, assuming that every side length is of unit distance or is of unit length, will be 0, 3, 2, 1. Okay. Now if I simply rotate this by 45 degrees, following 4 connectivity, I cannot generate the chain code for this figure, because these movements are not defined in my case. Or even if I take the concept of chessboard movement, okay. So these are the boundary points. This is one boundary point, this is one boundary point, this is one boundary point, this is one boundary point. So the kind of movement that I have to make is, assuming that this is my starting point, I have to make a movement over here, okay, which gives me 0. I have to make a movement over here, which gives me 3. I have to make a movement over here, which gives me 3 again. Movement over here, 2. Movement over here, 2. Movement over here, 1, 1, 0. So you find that here the chain code was 0, 3, 2, 1. Now my chain code is 0, 3, 3, 2, 2, 1, 1, 0. The chain codes are totally different. Okay. Though over here, it is simply a case of scaling. is it not? Earlier case I had every line segment only one appearance, now I have every line segment appearing twice. Okay, so you can say that it's just a matter of scaling. I can scale it down to have the same chain code. But what happens to 8 connectivity? If I go for 8 connectivity, let me see if they have different color. If I go for 8 connectivity, then this will be coded as 0, this will be coded as 6, this will be coded as 4, and this will be coded as 2. Okay. Whereas if the same figure is rotated by 45 degrees, this will be coded as 7, this will be coded as 5, this will be coded as 3, this will be coded as 1. Okay. Pardon? Yeah. So now it is visible. Okay. So you find that over here my chain code becomes 0, 6, 4, 2, and over here the chain code becomes 7, 5, 3, 1. Okay. So following 4 connectivity, though I could say that one is just a scaled version of the other, the moment I go for 8 connectivity, because this gives me more precision, the chain codes are totally different. Okay. So when I go for such chain code representation of boundary, you find that if I simply translate this figure, move from one position to another position, the chain code will remain the same. But if I rotate the figure, the chain code becomes totally different. So this sort of representation, boundary representation, is translation invariant, because it does not vary with translation. But it is not rotation invariant. It depends upon rotation. Right. Also, the problem of selection of starting point is over here. As I change the starting point, shift the starting point, the chain code again becomes different. Okay. So how to take care of these problems if I want to represent a boundary or a shape by chain code? Okay. So there is a concept of differential chain code. Okay. So to go for this differential chain code, let us start with the same figure. Let me take another page. Okay. So we are talking about differential chain code. So let us start with the same figure. Okay. Now over here, what I do is when I move from the first point to the second point, I don't give any code to this, right? When I move from the second point to the third point, okay, so here the code was supposed to be 0, right? And here the code was supposed to be 6, following 8 connectivity. So instead of giving this direct code, what I give is that how many rotations, either in the clockwise direction or in the anti-clockwise direction of the rotations in my coding scheme has to be made so that I move from 0 to 6. Okay. So you come to this coding scheme. Yeah. So this is 0 and this is 6. So if I follow anti-clockwise rotation, I have to move 1, 2, 3, 4, 5, 6 steps, right? So I code this as 6, right? However, to this I have not yet given any code. Now when I move from this to this was originally 6 and this is originally 4, right? So how many such rotational steps I have to perform? So this is 6, this is 4. So number of steps will be 1, 2, 3, 4, 5, 6. 6 again. So this also becomes 6. Right? From here to here, I have initially I had 4 and now it has to be 2. Right? Initially it was 4 and now it has to be 2. So again, how many steps I have to move? 1, 2, 3, 4, 5, 6. So again 6 steps. Right? And this was 2 and this has to be 6, this has to be 0. So 2 to 0, how many? 1, 2, 3, 4, 5, 6. Again 6 steps. So this 6, 6, 6, 6, that becomes my differential chain code. What happens in this particular case? Here my initial direction was 7, but I don't code it. Okay, the direction of movement was 7, same as this. Okay, what is the next direction? Next direction is 5. You come over here, next direction is 5. So from 7 to 5, how many rotations I have to perform? 1, 2, 3, 4, 5, 6. So I have to perform 6 rotations. I get that. Right? Now this was 5 and this is 3. 5, 3. How many rotations I have to perform? 1, 2, 3, 4, 5, 6 again. So this also becomes 6. So likewise, if you continue, you find that all these directions in the differential code will be 6 only. So this becomes 6, 6, 6, 6. This also becomes 6, 6, 6, 6. Okay, the codes are identical. Now it has become very simple. Only 6, 6, 6, 6, 6, 6, 6, 6, simply because my figure is simple. Right? If the figure is a complicated figure or an arbitrary figure, my code will not be as simple as that. Okay. So I'll get the differential chain code, which is rotation invariant, but even then the differential chain code does not remain starting point invariant. Depending upon the starting point, I'll have different chain codes for an arbitrary figure. So to take care of that, what we can do is, I can consider this code as a cycle. Instead of taking this as a chain, I can take it as a cycle. Once I have a cycle, I can decide where to cut that cycle so that I can have a numerical representation which is either maximum or minimum, and that becomes my chain code. Okay. So because now instead of a chain, initially I consider that to be a cycle, so it will be the starting point invariant. Okay, because cycle does not have any starting point or any end point. Then I enforce a starting point or end point depending upon a position, so that if I cut the cycle at that point, the numerical representation of the code that I will get will be either maximum or minimum. And because it is maximum or minimum, given a cycle, I can find out only one maximum or only one minimum, not multiple. Unlike I have a situation like this. I mean, wherever I cut this cycle, I'll get the same number. So it is having all maxima or all minima. That is only because this is symmetric and simple. But in case of arbitrary figures, I will not have that kind of unfortunate situation. So symmetricity, though we like it in our daily life most likely, but it makes our life hell whenever you go for such a kind of automation job. Pardon? This example, there is no problem. This example, because this is a very simple one. But when you work with the real life problem, you don't get such simple situation. You will have artificial figures. Okay. So we'll stop here today. Next day we'll continue with other features and feature description techniques. Thank you.